Consider f from r plus 2 close 4 to infinity given by fx equal to x square plus 4. Show that function is invertible with inverse f inverse of f given by f inverse of y is square root of y minus 4, where r plus is the set of all non-negative real numbers. Say here, function is from r plus to close 4 to infinity. This is set of non-negative real numbers. Codomain is close 4 to infinity, and this function is given by x square plus 4. Now to define a new function g, which will be its inverse, we require to determine a domain of that new function g. So whenever we find inverse of such functions or any function, we always try to find a new function g such that g of is identity function on domain of f and fog is identity function on domain of g. Then we can say g is inverse of f. But to define g, we require its domain, and in this method we always take range of f as domain of g. Range of f we have to take domain of g. So let us find what is range of f. So to find range of f, here see, function is working on a set of all non-negative real numbers. So from this formula it is clear that for all x belonging to domain of f, all x are non-negative. X is non-negative, so x square is greater than or equal to 0. We are creating this formula. Now adding 4 on both the sides. X square plus 4 is more than or equal to 4. So now this is fx. Fx is more than or equal to 4. So all images are 4 or more than 4. So therefore fx belongs to 4 to infinity. This is the set of images and it is range. So range is equal to 4 to infinity. Same as codomain of f. So same set we will take as domain of g. So this set will be domain of g. Now to determine formula for function g, what we do? For every y belonging to this range, now for all y belonging to this range, every element belonging to range of this function, every y will be fx. So suppose y is image of some x, x will be in domain of function f. So now from this statement we find value of x, y equal to fx. So y is equal to fx is x square plus 4. Therefore x square is y minus 4. So x is plus or minus root y minus 4. Now here this x, it will be in domain of function. So x is obviously positive. So here we take positive square root. We are not going to take negative square root. But x is in r plus, therefore x equal to root y minus 4. So value of x, this will be formula for a new function g, and now I am defining a new function g. So define, now we are defining g from, now domain of g, it will be range of this function. Whatever here we have found range, that we have to take codomain of, we have to take a domain of g, and codomain of g, it will be domain of f, r plus. So say here function was from a to b, and new function we are taking from b to a, because here b is itself range. If in any question, if range and codomain are not same, in that case range is subset of codomain. In that case, this codomain we don't take as domain of g, but we take whatever is range as domain of g. But because in this question range and codomain are same, that's why we are taking same. And formula for g, this function given by g of y equal to square root of y minus 4. From y equal to fx, whatever is value of x gives g of y. This value determines formula for g. So this is a new function g from b to a. Now to determine whether is it inverse of f, so now application of definition, we have to find compositions GOF and FOG. So let us find GOF. Now GOF, when finding GOF we require domain and codomain of GOF. Say domain of GOF, first function is f, so put here domain of first function. What is domain of first function? R plus, so we should keep here R plus, non-negative numbers. G is second function, so codomain of this composition will be codomain of second function. And what is codomain of G? It is R plus, so this will be R plus. So before finding formula for GOF, we have to fix domain and codomain. So this function will work on every element of R plus. So for all x belonging to R plus, that is domain, GOF of x equal to G of fx. Now this fx we are putting in formula for g. Here I am putting fx. So g of fx equal to root fx minus 4. So it is equal to square root of fx minus 4. G of fx is root fx minus 4. Replace y by fx. Now value of fx. Fx is x square plus 4. So we put here x square plus 4 minus 4 as it is. This is fx. So it is root x square. Square root of x square is modulus x. Now say x is non-negative. So modulus x is x because x is non-negative. So what is proved here? Therefore GOF is from R plus to R plus. GOF of x is equal to this is equal to x. So this function keeps input as it is. Whatever you keep here, output is same. GOF of 5 is 5, GOF of 7 is 7, GOF of 7.2 is 7.2. X is every non-negative. You can also put here 0. GOF of 0 is 0, GOF of 1 is 1, GOF of 1.6 is 1.6. That means any function if keeps elements unchanged and its domain and codomain are same, then that function is said to be identity function on this set. So this is identity function on R plus. So this first condition is verified. Now second condition. Second condition, FOG. FOG, so here we keep domain and codomain. Domain of first function. What is here first function? It is G. Its domain is closed interval 4 to infinity. Here codomain we keep codomain of second function. What is codomain of second function? Codomain of second function is 4 to infinity. So here 4 to infinity. So this function will work on elements of its domain. So for all x belonging to 4 to infinity, FOG of y, here we change variable, we take y. Here we have taken x, here we are taking y. So for all y belonging to 4 to infinity, you can also use x. But we keep a common habit. When finding GOF, we will use x. When finding FOG, we will use y as variable. So FOG of y is f of gy. Now in formula for f, we are putting gy. So here I am putting gy. So we keep here gy. F of gy is gy square plus 4. F of gy is gy square plus 4. See, formula was f of x is x square plus 4. So in that formula, x is replaced by gy. Now what is gy? Gy is root y minus 4. So here we keep value of gy, root y minus 4. Gy is root y minus 4. So it is y minus 4 plus 4. So what is it? Y. So here FOG is also keeping element unchanged. Therefore, FOG, it is from 4 to infinity to 4 to infinity, FOG of y equal to y. This function also keeps element unchanged and its domain and codomain are same. If any function has domain and codomain same, it keeps element unchanged, then that function is identity function on this set. So this is identity function on 4 to infinity. So second condition is satisfied. So by definition, from 1 and 2, from 1 and 2, here G is a function such that GOF is identity function, FOG is also identity function. So F inverse G is such function, G is said to be F inverse. So now we can replace here this symbol G by F inverse. So F inverse is a function from 4 to infinity, 4 to infinity, to r plus 4 to infinity to r plus given by f inverse y equal to f inverse y is square root of y minus 4. So when f of g is identity function, g of is identity function, then we say function is invertible. So from 1 and 2, here f is invertible function. I am inserting one statement, because g of is identity function, f of g is identity function. If we can find such function g, then therefore f is invertible. So from 1 and 2 we say f is invertible, and inverse of f is g. So g we have replaced by f inverse. So this is the method to find inverse. Consider function f whose domain is set of non-negative real numbers. Codomain is close minus 5 to infinity, given by fx is 9x square plus 6x minus 5. Show that this function is invertible with this formula. See, again we apply ditto method, similar method which we applied in last question. See here, function f is from minus 5 to infinity, given by fx equal to 9x square plus 6x minus 5. Now, because in this question also we are not given range of a function f, and we have to take range of f as codomain of a new function g. So let me check what is range of f, which we want as domain of g. So to find range of f, say here function is 9x square plus 6x minus 5. So to find images, because this is quadratic function, making this perfect square polynomial 9x square plus 6x, so last step should be 1. So this will be then perfect, this part will be perfect square polynomial, but we are given minus 5. So to maintain the value, subtract 6. 1 minus 6 is minus 5. So splitting this minus 5 as 1 minus 6, it is then 3x plus 1 whole square minus 6. Now x is positive for all x belonging to this non-negative real numbers, positive or it can be 0. So for all x belonging to r plus, x is more than or equal to 0. Now we are creating this formula in this form to check its range. So multiplying this by 3, so 3x is more than or equal to 0. Now adding 1, 3x plus 1 more than or equal to 1. Now taking square, any number is more than or equal to 1, then its square is also more than or equal to 1. Subtracting 6, so 3x plus 1 whole square, subtract 6 on this side, subtract 6 on this side. So this is formula for fx in this form. So this is fx. So fx is more than or equal to minus 5. So here fx belongs to close minus 5 to infinity. So range is close minus 5 to infinity, which is same as domain. codomain. So codomain of function is itself a range of function. So that's why this set, which is range of f, we will take codomain of G. So codomain is determined. Now for formula of G, procedure is for all y belonging to range. If y is in the range, if y is in the range of function, then obviously, because any number belonging to this set, it is set of images, so y will be fx. That means y equal to fx, and x will be from domain of f. What is domain of f? R plus. So this x will be in R plus. Now from this equation we are going to find value of x. Y equal to fx. Now fx is 9x square plus 6x minus 5. But in calculation, value of fx we are putting in this form: 3x plus 1 whole square minus 6. Continuing calculation to obtain value of x, 3x plus 1 whole square is equal to y plus 6. So 3x plus 1 equal to plus or minus square root of y plus 6. So 3x is minus 1, take 1 on that side, so minus 1 plus minus square root of y plus 6. So x is minus 1 plus minus square root of y plus 6 by 3. But say, here there are two possibilities, plus or minus. But if we take a minus sign, then what will happen? Here, minus 1 and minus of this value. So minus minus, that is negative. So x will be negative. If you add a negative number into negative number, negative negative, that is negative. Negative plus negative is negative, divided by 3 is negative. So in that case x will be negative. But here x is non-negative. So here plus sign, minus sign is not possible. Or after this step also we can determine that because x is non-negative, x is more than or equal to 0, so 3x is more than or equal to 0, so 3x plus 1 will be also more than or equal to 1, so it cannot be negative. So because x is in R plus non-negative, this minus minus is not possible, or here minus is not possible. So that we keep here with condition, but x belongs to R plus. So x is minus 1. Now we don't take both minus, here we take plus square root of y plus 6 upon 3. So this formula means this value of x, it gives formula for G, and this gives domain for G, which we are now defining. So now define function G whose domain is minus 5 to infinity, its codomain is R plus, given by G of y equal to minus 1 plus root y plus 6 upon 3. So a new function is defined. Now let me check compositions. What is GOF and what is FOG? So first of all, GOF. When finding GOF, domain of GOF, that is domain of first function, What is domain of first function? R plus. Codomain of second function. Codomain of second function is here, R plus. So G of f will take values from R plus. So for all x belonging to R plus, G of f of x equal to G of fx. Now we want G of fx. G of fx. Now here I am putting fx. So I should keep here fx. So G of fx is -1 plus root fx plus 6 by 3. So -1 plus square root of fx plus 6 by 3. Y is replaced by fx. G of fx is -1 plus root fx plus 6 by 3. Now we keep value of fx. What is fx? This is fx. Now I am putting here value of fx. So -1 plus square root of fx is 9x square plus 6x minus 5. This is fx and plus 6 as it is. So fx plus 6 upon 3. So it is -1 plus square root of 9x square plus 6x plus 1 upon 3. So that is -1 plus square root of, this is 3x plus 1 whole square upon 3. But say x is non-negative. X is non-negative, so 3x plus 1 is non-negative. So therefore this can be written as root t square is modulus t. Root t square is modulus t. But because t is positive, t is non-negative, x is non-negative, this number is non-negative, so 3x plus 1 is non-negative. So if t is non-negative, modulus t is t. So now this is equal to t because 3x plus 1 is non-negative. So this is 3x by 3. Therefore it is equal to -1 plus 3x minus 1 plus 3x plus 1. -1 is cancelled, so 3x by 3. So it is x. So what is proved? GOF of x is x. Therefore GOF is from R plus to R plus, and GOF of x equal to x. So this function keeps element unchanged. Domain and codomain are R plus. So this is identity function on R plus. First condition is satisfied. Now second condition. Second is about FOG. To find FOG, here we take domain of first function. What is domain of first function? Domain of G is -5 to infinity, and codomain of second function. Codomain of second function is -5 to infinity. So here domain of G, codomain of F. Here codomain of F itself is range. Range and codomain are same. So -5 to infinity, -5 to infinity. Now for all y belonging to -5 to infinity, we are finding FOG of y equal to f of gy. Now in formula for f we are putting gy. So f of gy, so here we are putting g of y. Here I am going to put g of y, or we can also put here g of y. Here also, in this form also we can put g of y. Let me put here g of y in this form. So calculation becomes simple. So see f of gy. So f of gy, now x I am replacing by gy. So f of gy is 3 times gy plus 1 whole square minus 6. So I am putting here gy. Clear? X is replaced by gy. So putting here gy. So 3 times gy plus 1 whole square minus 6. Now value of gy 3 times. Now what is gy? Here it is gy. So minus 1 plus square root of y plus 6 by 3 plus 1 whole square minus 6. So this 3 will be cancelled. Then what is left? Minus 1 plus root y plus 6 plus 1. Then this minus 1 plus 1 will be cancelled. So what is left? Root y plus 6 whole square minus 6. So it is equal to y plus 6 minus 6, it is y. So what is proof? FOG of y is y. Therefore FOG is from minus 5 to infinity, minus 5 to infinity to minus 5 to infinity, and its formula is obtained FOG of y equal to y is derived. FOG of y is derived. Therefore this function is identity function on minus 5 to infinity. Second condition. So GOF is identity function on domain of f. FOG is also identity function on domain of G. Therefore from 1 and 2 it is clear that this function is invertible. Therefore f inverse is G. Therefore now here I replace G by f inverse. So f inverse is from minus 5 to infinity to r plus given by f inverse of y equal to minus 1 plus root y plus 6 by 3. So it is required inverse. So this is derived root y plus 6 minus 1 by 3. Find number of all 1 functions from the set containing n natural numbers to itself. Also find number of all onto functions from the set containing n natural numbers to itself. See, to understand this question, I am taking diagram. This is first set containing n natural numbers, and function is set from this set to itself. Again repeating this set is repeated. Up to n. Let me say this set is A, this set is A, set A to A itself. Now see, Question is find number of 1 1 functions. So see, for 1 1 function we need correspondence, 1 1 correspondence. We don't want many 1. See, in function every element of first set is associated uniquely with element of second set. So doing that procedure, 1 can be associated with 1, it can be associated with 2, it can be associated with 3, it can be associated 4. So 1 can be joined with any 1. 1 can be joined with any 1. We can't join 1 with more than 1 elements. If you join 1 with this 1 and with this 3, then this is not function. 1 many relation is not function. Any element of first set should not be associated with more than 1 element. Otherwise this is not a function. This is not allowed. So every element must be associated uniquely. This is allowed. Or you can associate 1 with 2, or you can associate 1 with 3. So 1 has n choice. 1 can be associated by n ways. If you join 1 with 4, then you can't join 1 with any other element. Only 1 arrow from each element of first set. So here 1 can be associated by 1 way, n ways. 1 can be associated by n ways. This can be joined with 1, it can be joined with 2. So for 1 there are n choice. It can be associated by n ways. Now turn off 2. Now you can't join 2 with 4. If you join 2 with 4, then this is not a 1 1 function. It will be then many 1. We don't want many 1. So you can't join 2 with 4. Except for you can join 2 with any number in second set. So 4 is connected out of n numbers. Now how many are left? So here n minus 1 numbers are left. So 2 has n minus 1 choice. 2 can be joined with 1, 2 can be joined with 2, 2 can be joined with 3, 2 can be joined with 5, 2 can be joined with 6, like this. Suppose 2 is connected with 1. So 2 can be joined. It can be associated by n minus 1 ways. Now there is turn of 3. Now 3 cannot be joined with 1, 3 cannot join me with 4. Otherwise it will not be 1 1. So for 3 there are 2 less choice. Total n choice. So except these 2, how many choices are left? N minus 2 choices are left. So 3 can be joined with any number from this left n minus 2 numbers. So 3 can be associated by n minus 2 ways. Suppose 3 is connected with 2. Now 3 is connected. So 3 choices are taken out of n. Out of n, 3 are taken. Now how many are left? N minus 3 are left. So for next number there are n minus 3 choices left. So 4 can be joined. 4 can be associated by n minus 3 ways. Suppose 4 is connected with this number. So continuing this procedure, At last, here last value when n will be left, so on this side only one number will be left, so n can be associated by only one way. Here see these numbers are connected, so for n there will be only one choice left. So this procedure gives not only number of 1 functions, but it also gives onto functions. So therefore total number of 1 functions equal to this action by n ways, second action by n minus 1 ways, third action by n minus 2 ways, and last action by 1 way. So it is product of first n natural numbers, so it is n factorial. So if first set has n elements, second set has n elements, then total number of 1 functions n factorial. And here it is clear that for onto function also it is same procedure, because here number of elements are same which are in domain, same is number of onto functions. So here number of onto function is also same. So whenever you want a total number of 1 and a total number of onto functions from set A to itself, and if that set contains n numbers, then total number of 1 functions n factorial, onto functions n factorial. If this set contains 10 natural numbers, here there are 10 natural numbers, in both sets there are 10 natural numbers, then total number of 1 functions 10 factorial, onto functions 10 factorial. If both sets have same number of elements, n elements, then number of 1 functions n factorial, onto functions also n factorial. Then see, in this question, set A has 4 elements. Set A has 4 elements. Suppose we are showing in this diagram. Set B has 2 elements. Find 1 functions. Say for 1 function, suppose I am joining x1 by y1. Now if I join x2 by y1, this is not allowed. Otherwise this is not 1 function. It is becoming many 1 function. We want 1 function, so this is not allowed. So x2 cannot be joined by y1, so if we join x2 by y2, this is allowed. But then coming on next, x3, these still 2 elements in first set are left, and to be this function, every element must be associated with someone. So association of these elements with someone is must. So if you join x3 with y2, then this is not 1. If you join x3 with y1, also not 1. So this is happening. If you try to obtain functions here, because this set has less number of elements, then number of 1 functions is 0. No 1 function is possible. So remember one note, that if A has m elements and B has n elements, set A has m elements, set B has n elements, and now here differing statements. If number of elements in set A is greater than elements in set B, then total number of 1-1 functions from A to B is 0. So say here in this question, in set A number of elements is more than that of in B, so number of 1-1 function is 0. So here number of elements in set A is more than that of in B. So number of onto functions, number of 1-1 functions from A to B is 0, like this. 4 elements, M is 4, here 2 elements, 4 is more than 2, so number of 1-1 function is 0. Now see, sometimes what happens, suppose the second statement which I want to explain, if M is less than N, if N is less than N, if M is less than N, then total number of one functions from A to B. See, explaining here by one example. Suppose here I am taking x1, x2, x3, x4, 4 elements. Here I am taking y1, y2, y3, y4, y5, y6, y7 elements. Defining function from A to B. A has less number of elements. M is 4, N is 7. 4 is less than 7. Now creating 1-1 function. X1 can be joined by how many ways? 7. X1 can be joined by 7 ways. It can be joined by y1, it can be joined by y2, it can be joined by y3. So suppose we are joining with y4. So x1 can be joined by 7 ways. Now x2 can be joined by remaining 6 ways. 6 elements are left. Suppose it is joined with y1. So 6 ways. x3 can be joined by, now how many choices are left? 5 left. 5 ways. 1, 2, 3, 4, 5. Suppose x3 is connected here. Then x4 it can be joined by 1, 2, 3, 4 ways. Suppose it is joined with y2 by 4 ways. See here, this is 1-1 function. Obviously it is not onto, because these are not images. These 3 numbers are not images. It's a function. It's a 1-1 function, but not onto, because these are not images of anyone. But whatever you can see here, it is 1 1 function. If number of elements in set A is less than that of in B, then 1 1 function is possible. Say here how many 1 1 functions are possible? x1 by 7 ways, x2 by 6 ways, we have performed this procedure. So total number of 1 1 functions is, this is 7p4. 7p4. 7 into 6 into 5 into 4. So here we can put formula for this rule, that if m has less than n, then total number of 1 1 functions from A to B is, say here the number was 4, here number was 7. So what is it? It is npm. What is it? npm. This is m is less. So npm, So remember these two statements. If m equal to n, then it is clear. If m equal to n, then number of 1 1 function is n factorial, or you can say m factorial. You can see these three cases: m more than n, m less than n, and m equal to n. Now we are talking about ontoness. In this question, how many onto functions are possible? For onto function, first of all, we find here total number of functions. So total here, total number of functions. We are finding a total number of functions, whether it is 1 1 or not 1 1. Obviously here there will not be 1 1 function. So whatever will be total number of functions, no one will be 1 1. All functions will be many one. So total number of functions, x1 can be joined by two ways. x1 can be joined by two ways. x2 can be joined by two ways. x3 can be joined by two ways. x3 can be joined by two ways. So total 16 functions. Now out of 16 functions, here I am showing functions which are not onto. So out of 16 functions, following functions are not onto function. Say which functions are not onto. Say here in set A, these are 4 elements. In set B, these are 2 elements. If connection is like this, x1 is connected with y1, x3 is with y1, x2 is with y2, x4 is with y1, then this is onto. This function is onto because both are images. But if all these 4 numbers are connected with y1, image of all 4 functions is only y1, then in this case y2 is not image of anyone. This is not onto. This is not onto. Similarly, if we connect all these elements with y2, suppose all entries, if I connect with all elements of first set, if I connect with y2, suppose if I show by this way, then here y1 is not image of anyone, so this is also not onto. So there are 2 functions. So out of 16 functions, following 2 functions, are not onto functions. And remaining functions will be like this, except these two diagram, except these two designs. The remaining designs, in all remaining designs, in remaining 14 designs, both will be in connection. So remaining all 15 functions are onto function. So total number of onto functions, therefore total number of onto functions equal to 16. Total functions are 16. Out of 16 exclude these two. So remaining 14 are total number of onto functions. Let f from R to R be defined as fx equal to 10x plus 7. Find function g from R to R such that g of f equal to f of g is identity function on R. Say here f is from R to R, fx is equal to 10x plus 7. This is a linear function. Here for every x belonging to R, fx is also in R. So this function, it's a codomain, it will be equal to range. For all x belonging to R, if x is any real, here for all x belonging to R, 10x plus 7 is a real number. So fx is here a real. So here range of this function is R, which is codomain. Now for all y belonging to range, if y is in R means y is in range, y is fx. If y is any element in R in range means it will be fx. So we take y, it will be some x, image of some x under f. Y is fx, y is fx, so y is equal to 10x plus 7. So x is y minus 7 by 10. This value of x, it gives formula for function g. Now we are defining a function g whose domain is range of a function. So domain of g will be range of function, codomain is domain of function, that is R, given by g of y equal to y minus 7 by 10. Therefore this is a new defined function g. Now for this g we check these conditions. So now g of f, say here g is from R to R, f is also from R to R, so g of f will be also from R to R. For all x belonging to domain of a g of f, g of f of x, it is equal to g of fx. Now I put here fx, so I should keep here fx. So g of fx is fx minus 7 by 10. So g of fx is fx minus 7 by 10. Now fx is 10x plus 7. This is fx minus 7 upon 10. So what is it? It is equal to 7 7 cancel, 10x by 10 is x. So GOF of x is x. That is proved. Therefore GOF is from R to R. GOF of x is x. This is identity function on R. Therefore GOF is identity function on R. So this condition is satisfied. Now we check for FOG, and FOG, it is also from R to R. For all x belonging to R, FOG of y, FOG of y is f of gy. Now f of gy, in formula for f we are putting gy. I am putting here gy. F of gy is 10 times gy plus 7. So f of gy is 10 times gy plus 7. Now putting value of gy. So 10 times gy is, this was formula for gy, y minus 7 by 10, and here plus 7 as it is, this plus 7 as it is. So here 10 10 cancel, y minus 7 plus 7, that is y. So FOG is, therefore FOG of y is also y. So FOG is from R to R, FOG of y is y. So this is also identity function or R. So second condition is also satisfied. Therefore from 1 and 2 G function, it is from G function from R to R, G of defined by G of y equal to y minus 7 by 10 is required function satisfying given conditions. In short, if any function g satisfies both conditions, then what we say, g is inverse of f. So say here we can say f is invertible. We can say f is invertible and inverse of f is g. So inverse of f, it will be from R to R, f inverse of y is equal to y minus 7 by 10. So this function, this question, it can also be asked by this way. This question can be also asked by these words, that f is from R to R, fx equal to 10x plus 7. Prove that this function is invertible. So f is from R to R, fx equal to 10x plus 7. Show that f is invertible and find inverse of f. So this question can also be found by, it can also be given by these words. So answer is same, method of asking question is different. Say function here in this question, Set A is given, set B is given, two functions whose domain are same, codomain are same, and these formulas are given here. Fx is x square minus x and gx is 2 times modulus x minus half minus 1. Question is, are f and g equal? Justify your answer. Now see, two functions are said to be equal functions if these three conditions are satisfied. Their domains are same. Their domain are same. Their codomain are same. And for all A belonging to their domain are same. So this is same set. For all A belonging to their domain, f of A is equal to g of A. Two functions f and g, here I am adding this word, f and g are said to be equal if their domain are same, their codomain are same, and f of A equal to g of A for every element of domain. So let me check this condition. Keep remember this note. Here domain are same. Domain of f and g is A. Codomain of f and g is B. So it is clear that these conditions are satisfied. So only the left work is we verify third condition. So to verify third condition, first of all I am finding images of elements by function f. So see, for all here set A is minus 1, 0, 1 and 2. This is domain of f and g. So domain of f and g, here domain of f, domain of g, their domain is set A. It is A containing minus 1, 0, 1, 2. So both functions will work on elements of this set A. First of all, here f of minus 1, f of minus 1, then we will find f of 0, then f of 1 and f of 2. Now formula for fx. Fx is x square minus x. So fx is x square minus 1. Here let me make a space for that statement fx. Fx is x square minus x. Now in this function I am putting minus 1, then 0, 1 and 2. F of minus 1, f of 0, f of 1, f of 2. And we are also given formula for gx. Gx is 2 times x minus 1 by 2. So first of all we find by this formula images. F of minus 1 is minus 1 square is 1 minus minus 1, that is plus 1, so it is 2. F of 0 is 0 minus 0, that is 0. F of 1 is 1 minus 1, 0. F of 2 is 2 square is 4, 4 minus 2, that is 2. Now this side we find g of minus 1, g of 0, g of 1, g of 2, g of minus 1. So 2 times minus 1 by 2. So 2 times, this is 3 by 2. Minus 1, sorry, here I missed this number. 2 times modulus x minus half, minus 1 is here. So here 2 times x minus half minus 1. So this is 2 times 3 by 2 minus 1, so it is 2. G of 0, put here 0. So 2 times 0 minus half minus 1. So this is 2, it will be cancelled. Modulus of minus 1 is 1. So 1 minus 1, that is 0. G of 1. G of 1 is 2 into 1 minus 1 by 2 minus 1. So 2 into 1 by 2, that is 1. 1 minus 1 is 0. G of 2. So 2 into 2 minus half minus 1. Say we are putting value in this formula. So this will be 3 minus 1, that is 2. So say, look here. F of minus 1 is 2. G of minus 1 is also 2. Here f of minus 1 equal to g of minus 1. F of 0 is 0. G of 0 is 0. F of 0 is g of 0. F of 1 is g of 1. F of 2 is g of 2. Therefore, for all elements of domain, for all x belonging to A, f of A equal to g of A. F of minus 1 is g of minus 1, f of 0 is g of 0, f of 1 is g of 1, f of 2 is g of 2. That means for all elements of set A, f of A is g of A. So this condition is also satisfied. So here domain and codomain are same, and codomain of f equal to codomain of G. Codomain is also B. So domains are same, codomains are same, and this is satisfied. So from 1 and 2, this statement is 1. We say this is 1, this is 2. Second condition. This is 3. So from 1, 2 and 3, from 1, 2 and 3, it is clear that f and g are equal functions. Let f is function from w to w be defined as fn is equal to n minus 1 if n is odd. Fn is n plus 1 if n is even. So that this function is invertible, and find inverse of f. Here w is the set of all whole numbers. Say here w is set of whole numbers, that means all natural numbers including 0. That means non-negative integers, whole numbers. Function is from w to w, f of n is n minus 1 if n is odd, and fn is n plus 1 if n is even. So here If we try to understand in the diagram, then see what is happening. W to W, 0, 1, 2, 3, 4, 5, 6, 7, 8. These are numbers in domain, in codomain. If input is odd, output is 1 less. See, if you keep here 1, so f of 1 is 1 minus 1, 0. Image of 1 is 0. If you keep 3, image of 3 is 3 minus 1, that is 2. If you keep 5, so its image is 4. Image of 7 is 6. Image of 8 is 7. Sorry, image of 9 is 8. First of all, we are taking odd inputs. For odd inputs, this is happening. Now, if input is even, if you keep here a even number, then output is 1 plus. So, image of 0, so 0 plus 1. So, image of 0 is 1. Image of 0 is 1. Image of 2 is 3. Image of 4 is 5. Image of 6 is 7. Image of 8 is 9. Now observe this design. If you select any two distinct inputs, their images are equal. Sorry, images are distinct. Distinct input, distinct output. Select any two inputs. If both are odd, their images are distinct. If both are even, then also their images are distinct. If any one is odd, any even, their images are distinct. So from this diagram, it is clear that this function is 1, 1. Now how to show in words, how to put steps to prove it is 1, 1. So we are going to use definition that for every n1, n2 belonging to domain, if f of n1 equal to f of n2 implies n1 equal to n2, then function is 1, 1. Or same definition in different word, n1 not equal to n2 implies fn1 not equal to f of n2, then also it is said to be 1, 1. So whatever is happened here, now we are putting in words using this procedure. So here function is working by two style. If inputs are odd, inputs are even, so we differ cases. So case 1, for 1, 1-ness, let me take case 1. If n1 is even, if n1 is, suppose we take odd, n1 is odd and n2 is even. If n1 is odd, n2 is even, or take both odd, let me take both odd, then in second case we will take both even, then we will take one odd, one even. So if both are odd, then beginning from fn1 equal to fn2, both are odd numbers. That means if inputs are odd, say n1 is odd, n2 is odd, both are odd. So if both are odd numbers, then suppose that fn1 equal to fn2, we are going to prove n1 equal to n2. So fn1 equal to fn2, because n1 is odd, f of n1 is n1 minus 1. n2 is odd, f of n2 is n2 minus 1. So n1 equal to n2. So in case 1, what is proved? fn1 equal to fn2 implies n1 equal to n2. Now case 2. If n2 is even, n1 is even, n2 is even, both are even, n1 and n2 both are even. Second case, suppose n1 is e1, n2 is e1. Then what happens? If n1 is e1, n2 is e1, performing similar procedure, let f of n1 equal to f of n2. n1 is e1, so f of n1 is n1 plus 1. n2 is e1, so f of n2 is n2 plus 1. So n1 equal to n2. So here also f of n1 equal to f of n2 implies n1 equal to n2. So in case 2 also proved it is 1 1. Now case 3. If n1 is odd and n2 is e1. n1 is odd, n2 is e1. If n1 is odd, n2 is e1, then obviously this means n1 not equal to n2. So in this case, f of n1 is odd, so f of n1 is n1 minus 1. F of n2 is e1. n2 is e1, so f of n2 is n2 plus 1. So say n1 is odd. Odd minus 1 is e1. n2 is e1. If you add 1 in e1, so e1 number plus 1, that becomes odd. So this is odd. So here n1 not equal to n2, and you can see that f n1 is e1, f n2 is e1. Therefore f n1 not equal to f n2. Here it is clear, e1 not equal to odd, so f of n1 not equal to f of n2. So this means what is proved? So here n1 not equal to n2 implies f of n1 not equal to f of n2. If these numbers are distinct, their outputs are also distinct. So in case 3, this is applied. In case 1 and 2, this is applied. Meaning is same. So from case 1, 2 and 3, so we can say that from case 1, 2 and 3, it is clear that for all n1 and 2 belonging to W, f of n1 equal to f of n2 implies n1 equal to n2. Or we can say same statement by this way, n1 not equal to m2 implies f of n1 not equal to f of n2. So function is 1 1. Therefore this function is 1 1 function. So we have proved that this function is 1 1 function. Now we are going to check ontoness for onto function. Now see, once again I am coming on diagram. Just we discussed. See here, this is domain, this was codomain, 0, 1, 2, 3, 4, 5, 6 like this. 0, 1, 2, 3, 4, 5, 6 like this. We discussed that image of odd Image of odd is 1 less. Image of 1 is 0. Image of 3 is 2. Image of 5 is 4. Image of 7 is 6. So this is odd number. These numbers, these are odd. Image of odd is E1. Image of odd is E1. Image of any odd is 1 less. Now think in reverse process. Pre-image. See, pre-image of E1 is odd. Pre-image of E1 is odd. See, here this is E1. This is E1. If you observe any E1, then its pre-image is odd. But one more. So here, if n is E1, these are E1, then its pre-image, see what is its pre-image? It is one more. Pre-image of 6 is 7, pre-image of 4 is 5, pre-image of 2 is 3, pre-image of n is n plus 1. These are E1. So its pre-image is odd. This is odd. So first of all, I am putting this statement. Say here, for ontoness, we are going to show that every element of codomain is image of someone in domain. So first of all, discussion is for E1. If for all, if n is any even integer, if n is any even integer, if n is any even integer belongs to codomain, n is any even integer belongs to second set. So for all such n, for all n E1 which are in codomain, correcting this statement, for all n equal to even integer belonging to codomain, there exists n plus 1 which is odd in domain. There exists n plus 1, it will be odd in domain, such that image of n plus 1 under f is n. Image of 5 is 4, image of 3 is 2, image of n plus 1 is n. So such that f of n plus 1 equal to n. Now same statement we are putting for odd number. Say this is odd, this number is odd, this number is odd, this number is odd. Now look odd numbers from codomain. See, if you put here even input, then output is one more. Image of 0 is 1, image of 2 is 3, image of 2 is 3, image of 4 is 5, image of 6 is 7. So when input is even, output is odd. That means for odd output there exists input. Output is odd, input is even but one less. Now focus on odd numbers. Focus on odd numbers. If any odd is selected from codomain, then its pre-image is E1 but one less. If this is n minus 1. So here if n is odd, then its pre-image is one less. N is odd, this is E1. So under F, this is happening. So similar statement for all n odd integers, all taken from codomain. There exists one less, which is E1, belongs to domain such that image of n minus 1 is n. So say from statement 1 and from statement 2, what we can say, combining these statements, that for every integer, whether it is even or odd, for every integer belonging to codomain, there exists some x, there exists a pre-image in domain. So here range is codomain. Every element of codomain is image, that is proved. So from 1 and 2 it is clear that, so from 1 and 2 it is proved that for every n, whether it is even or odd, belonging to codomain. What is codomain? Set of whole numbers. There exists its pre-image. Its pre-image in domain. What is domain? Set of whole numbers. So that means this function is onto function. Therefore, given function is an onto function, and if function is 1 1 and onto both, its inverse exists. Already we proved that function is 1 1, and here we have proved that function is onto. So thus this function is 1 1 and onto both, therefore f is invertible. Now we keep formula for inverse. So f inverse will be, f was from W to W, so f inverse will be from W to W. And from this statement, say y equal to fx. So x is f inverse y. So from this statement what we can say? Here n was E1. Okay. So f inverse n equal to, see f I have taken on this side. So f inverse n equal to n plus 1. If n is E1, here n was E1, and in this case, second statement, for n odd, f inverse n equal to n minus 1 if n is odd. So this is inverse of function.